Distribution transformers reduce the high voltage electricity from the supply network to voltages that are safe to use in homes and businesses. Pole-top transformers are usually connected to the primary supply network via a cutout fuse that protects customers and distribution equipment from overloads. Fault currents from the distribution network and evolving faults within the transformer will cause the fuse to operate. When an overload results in permanent damage to the transformer's internal components, an internal fault has occurred. Transformers are one of the most widely used components in the distribution grid. In the United States alone, there are approximately 50 million pole-top distribution transformers in service. 3 to 5% of them are re-energized every year, making it one of the most common operations for linemen. Lightning is still the leading cause of transformer failures. Other causes include manufacturing defects, mechanical damage, and different current-related failures. Recent improvements in transformer design make it more challenging and time-consuming for linemen to identify internal faults because they're not evident from the outside. The explosion seen here is an example of the hazards line workers may face when re-energizing transformers that have an internal fault. If the internal fault is undetected and the transformer is re-energized, the risk of explosion increases due to the resultant contamination in the oil. To efficiently identify faulted transformers and avoid their re-energization, IFD Corporation has developed a device called the Internal Fault Detector, or IFD. The IFD is installed on the side of the transformer, above the oil level, and does not interfere with any of the electrical components inside the transformer. This graphic shows an IFD sensor. It is a purely mechanical device requiring no electrical connections. The IFD serves a dual purpose, as a pressure relief device, or PRD, and as a fault detector. Here's how the IFD works as a pressure relief device. During a hot day or heavy loads, the transformer heats up. This causes a slow rise in the pressure, which will activate the PRD should the pressure go above the specified PRD activation value. As shown here, the heat rises in the transformer, causing pressure to build up slowly. As the pressure increases, it is able to equalize on each side of the diaphragm through the metered hole. Once the tank pressure builds up, the PRD opens, allowing air to escape. The PRD will close once the pressure is reduced. This operation will continue until the transformer cools down. Note that the IFD pressure relief device can be operated the same way as other transformer pressure relief valves. Now, let's look at how the device works as a fault detector. When a fault occurs, there's a sudden increase in tank pressure, and gases collect in and above the oil. The fault produces several types of gases. When these gases mix in particular proportions, they become explosive. In this graphic, the IFD is in the normal position. After a fault, there is a sudden increase in tank pressure. The metered hole will not allow equalization of pressure on each side of the diaphragm if the pressure increases suddenly. The rapid difference in pressure causes the diaphragm to move up, releasing the locking pin, which triggers the highly visible indicator flag to pop out of the side of the transformer. Once activated, the IFD will indicate to the line worker that there is an internal fault in the transformer and that it must not be re-energized. Note that the highly visible indicator flag cannot be reset. The highly visible flag has been designed for easy identification in daylight and also in the dark with a flashlight. An IFD-equipped transformer with a highly visible flag protruding must be taken out of service and replaced. Installing transformers with an IFD is no different than installing ones without an IFD. All the same fault checks and precautions must be made before energizing the transformer. The only difference in the installation process is the removal of the shipping lock once the transformer is mounted. If the fuse cutout is open, but the IFD has not been activated, chances are the transformer is okay to re-energize, providing all normal fault checks are done. Nothing can be considered 100% when it comes to safety. To give you an idea of how often transformers fault, let's look at the reports from a large North American utility. This utility was selected because of the area's diverse weather conditions, providing a representative sample of the industry in general. This utility documented that it did over 20,000 transformer re-energization operations in 1 year. Of these, it was calculated that 4,000 operations involved transformers with some sort of internal fault where the transformer was replaced. The line crews spent a significant amount of time trying to determine the problem with each transformer, translating to many hours of service outages. Had IFDs been installed on these transformers, the line crews would have known immediately which transformers needed to be replaced due to internal faults. Furthermore, according to this utility's statistics, 1 in every 250, or in this case 16 of these transformers, could rupture or explode in 1 year. To reduce the risk of significant events, utilities have developed thorough but time-consuming procedures. Unfortunately, these procedures are not always followed because of the need to restore power quickly. In the case of an event, related costs could include occupational health and safety worker wages, legal costs, environmental damage, cleanup costs, asset replacement, as well as potential fines and negative public relations. These costs are always extensive and range from hundreds of thousands to millions of dollars. From an asset management perspective, when using IFDs, fewer good transformers are taken out of service, reducing repair costs, transportation, and stock inventory. IFDs are inexpensive to purchase and easy to retrofit in transformers that are returned for repair. From a customer service perspective, a utility that uses IFDs can restore power faster. And from a network reliability perspective, restoring power quickly reduces the utility's System Average Interruption Duration Index, which results in increased quality of service and additional cost savings. The reliability of the IFD sensor has been confirmed through extensive laboratory conditions testing at PowerTech Labs, BC Research Council, and BC Hydro, as well as through system-wide in-service testing in small and very large utilities. Reliability tests were conducted for operation at temperatures down to -40°C, simulated fault current, impulse, moisture ingress, day and night visibility, and transportation. Strict inspections in the manufacturing process of the IFD assure consistent quality of the product and high-level performance to meet customer requirements. The IFD is in service across North America and Asia. Customers are satisfied with the IFD based on its performance during actual outages and the resulting service improvements. The IFD is listed in various distribution transformer standards guidelines as a substitute for the pressure relief valve. So to recap, according to industry studies, 1 in 5 transformer re-energization operations involves a transformer with an internal fault. The IFD will display a highly visible flag indicating which transformers are faulted. The benefits in the rapid detection of these faults include increased line crew productivity, improved network reliability and customer service, extended asset life, avoidance of environmental damage, and of course, increased job safety. As modern utilities strive to continually improve the efficiency of supply networks, the IFD is the next key implementation to enhance the performance of your distribution infrastructure.